morning. So today I'd like to actually pick up on the question that was asked by the young woman over there in the previous lecture on how we assign, how we name our tetrahedral stereogenic centers. And there's a nomenclature system called Von-Engel-Prelog nomenclature that basically allows us to assign what you can arbitrarily call right-handed or left-handed stereochemistry. That's a convention and everyone follows it. As long as we're all on the same page, then we all have the same way of talking about the molecules and the stereochemistry. Just like if everyone called a 3-carbon alkane butane, it would be butane instead of propane. So we're going to learn this nomenclature system today, and we're also going to get more familiar with molecules with multiple tetrahedral asymmetric centers. All right, the basic nomenclature is really very simple. Nomenclature consists of R and S to designate the stereochemistry. You can think of R, its Latin term is rectus, which means right. And we're going to learn that that also means clockwise. The left-handed notation is from Latin sinister. And we're going to learn that as synonymous with counterclockwise. All right. What I'm going to try to do, just as in nomenclature, naming alkanes and various other compounds, there's a series of rules to follow. I'm going to try to take us through those rules, and I'm also going to make it as simple as possible. Now, there's a lot of meat to stereochemistry. It's really, for those of you who have been, there's some fun, there's some three-dimensionality. It's really a deep topic. I have a book that's about 1,400 pages just on stereochemistry. And so one of the things that I want to do is to digest the topic and break it just at a simple level into some small bite-sized pieces. So come along with me on this journey. All right. So, first thing we need to do is identify the tetrahedral stereogenic center. That's pretty easy. So usually a carbon atom with 4 different things on it. Let me start with the word identify. And then what we need to do is to rank the substituents. All right, let's take an example, and we're going to take the 2-butanol that we used before as an example, so I'll write that again. So, pretty obviously, the carbon with the hydrogen, the hydroxy group, the methyl group, and the ethyl group is the carbon, the only carbon in 2-butanol that has 4 different substituents on it. So this is A, and in this case, the only tetrahedral stereogenic center. to do is to figure out the priorities of the substituents. The first way we rank priority, the most important way, is by atomic number. The highest atomic number gets you the highest priority. The lowest atomic number gets you the lowest priority. Kind of makes sense. You look in your periodic table, oxygen is at 8, carbon is at 6, hydrogen is at 4. So for priorities, it's pretty easy to see that our OH, the oxygen on here, is going to be 1. I'll just put an arrow here, highest atomic number. And our hydrogen then is going to be 4. I'll put an arrow here, lowest atomic number. Now we're faced with the situation of the methyl and the ethyl group, and they're both carbon. So our first ranking is at the atoms attached, they're the same, they're both carbon. So what we do now is we move outward, away from the tetrahedral stereogenic center, and we identify what's attached to those carbons. So both of these are carbon, all right, C and C here, but attached to this carbon is 3 H's, H, H, H. Attached to this carbon, we don't count this carbon anymore, we're just moving outward. Attached to this carbon moving outward is another carbon and 2 hydrogens. So this one is C, H, and H. And now we just look, okay, they were both the same atomic number. But moving outward now, we have a higher atomic number, carbon 6, attached to this carbon than we do to this carbon. So this substituent, the ethyl group, gets a ranking of 2. And the methyl group gets a ranking of 3. So the first rule we can say is higher atomic number leads to higher priority. And realize that when you then are comparing atoms of the same atomic number, you just move outwards. And that rule is going to get you pretty far. Just like in nomenclature, there's a lot of stuff that can be really arcane. I'm going to try to take us through the simplest and most relevant stuff. Now the next operation, once you've ranked the substituents, is just to look down the bond from the carbon atom, from the tetrahedral stereogenic center to the lowest priority atom. And then what we do is determine the direction 1, 2, 3 going around. Is it clockwise or counterclockwise? question?
I'm still a little bit confused. How do you tell the difference in priority between the ethyl group and the methyl group?
Question. How do we tell the difference in priority between the methyl group and the ethyl group? Both the ethyl group and the methyl group are carbon. So we know they're both at the same level there of their atomic number. So now we have to break the tie. And to break the tie, what we do is we move outward along the chain and say what's connected to each carbon. Connected to the methyl group is 3 hydrogens, all atomic number 1. Connected to the ethyl group, we're just moving outward, so I'm not counting the tetrahedral asymmetric center, is a carbon, the terminal methyl group on the other side, and 2 hydrogens making up the methylene group. So now we say in the tiebreaker, the ethyl group has the carbon on the right, has a carbon attached to it, and that trumps hydrogen attached to the other. So that gives us an assignment of 2 on the priority of the ethyl group and 3 on the priority of the methyl group, and of course we're 4 on the hydrogen and 1 on the oxygen. Other questions? These are good. These are really important to be thinking about at this point. What happens if you have the same groups on either side? So let us pretend for a moment that we had 2 ethyl groups. Somebody, what would we do in this case? It's not a stereogenic center. If they're the same group, then we don't have a tetrahedral stereogenic center. We need to have 4 different substituents. So in that case, we have a plane of symmetry in this molecule in 3-butanol, in 3-pentanol, and as a result, we know immediately that we don't have a chiral molecule. Other questions? All right, next thing is visualization. What we want to do is sight down, look down the bond from the carbon atom to the hydrogen atom in 2-butanol. And so I'm going to draw things out, and here's where, if you're not yet proficient with visualizing, here's where models can really help you out. So here's our OH is 1, our ethyl is 2, our methyl is 3, and I have this hydrogen going back. So we're looking down the bond to it, and I go 1, 2, 3. Our direction is clockwise. And that means our tetrahedral stereogenic center is R. So we call this compound R2-butanol. We always, by convention, put the R in parentheses. Let me do this with some video projection, because, as I said, we need to become proficient at this, and it takes a little bit of practice. Let's see if I have a model of R2-butanol. So I'm going to do this 2 ways. We'll take it slow. I'm going to show you how I do it, and then for people in the back, we'll do it on the video projection. So here's the model that I built. Please, if you have your models, pop yours together. No better time to get your exercise and visualizing than right now. right, so, hold up your models. Let me see more of them. Steal one from a neighbor if you don't have yours. Make a friend. We just had a seminar speaker who was an undergraduate at UCI in 1995 through 1998. She's now a professor at the University of Toronto. And she was trying to decide whether to take the the Chem 51 or Chem 52 course. She ended up taking the Chem 52, and not only did she end up getting inspired to go on in chemistry, organic chemistry, because of that course, but she also met the man who became her husband in that class. So go to your neighbor, if you don't have models, and borrow a model or look on. All right. So I'm going to do this here, and then I'm going to do it up on the video projector. So here's my 2-butanol, and you notice we're looking down the CH bond. We go 1 for the oxygen, 2 for the ethyl, 3 for the methyl. That's clockwise. Let me put that up on video as well, just to make it a little easier if things are working properly. All right. So, here we are, you notice, and this is the key, because if you don't sight down the bond, if you sight in the wrong direction, you'll get it exactly backwards. So, our tetrahedral stereogenic center is in front, where my finger is. The hydrogen, the lowest priority substituent, is in back, where my finger is. We have the oxygen atom. Getting it mirror projected here. Yes. Right. All right. Yes. This is the one case where I think video ends up being a. Okay, 1, 2. That's weird. Okay, we're gonna stick to this on the model. So again. 1 for the oxygen. Everyone's looking down. Here's the oxygen. It's the same as on the blackboard. Here's the ethyl group. Here's the methyl group. And so from your point of view, it's 1, 2, 3. It's clockwise. It's R.
So this is telling you
the question is this telling us which direction? Well, you can take it 2 ways. Here I've given us a molecule and I've said, which way is it? If I said draw S, then you draw it in a particular way. And the way I always do it when I'm asked draw S or draw R is I go ahead and I simply draw one, because I don't know off the top of my head, check it, and if I end up not getting it right, then the trick is you just swap the 2 substituents. So, if I go ahead and simply swap 2, not 3, not 1, but 2 substituents, then that's what we call inverting the tetrahedral stereogenic center, or inverting the chirality of the molecule. And now I know that this molecule is the opposite. So this one is S2-butanol. Now you can do this a couple of ways. One way is you can simply do the rotation in your head. You can go ahead. I'm going to swap them on my plastic models. You can go ahead and do the rotation in your head and spin the molecule around. So in other words, I can go ahead and say, all right, I will just spin this around like so. And then, when I've spun it around, I'm sighting down the CH bond, 1, 2, 3, it's counterclockwise. But the other way you can do it is you can say, well, it's drawn this way, but I know if I reverse things, if instead of sighting down the bond to the lowest priority substituent. I'm citing from the bond with the lowest priority substituent in front instead of in back, then everything's reversed. So in other words, you look at this molecule as I'm holding it now with the hydrogen pointing right out at you and the oxygen and the ethyl group and the methyl group. The way I deal with this is simply I say, well, it's all backwards. So when I go 1, 2, 3, oxygen, ethyl, methyl, I'm going clockwise, but we're citing in the wrong direction on the bond, which means in reverse it's counterclockwise, and the stereochemistry is S. You can do it either way. There's 3 different things, all equivalent, that we've done. One is we've gone and said we can rotate the molecule and simply make a new drawing. Another way is to say, well, we know we got this molecule by simply swapping the oxygen and the hydrogen. And we knew when it was like this, it was R, because we were citing down the bond. So if we swap 2 substituents, we invert the stereocenter, and we go from R to S. Or you can go ahead and say, well, I'm citing it backwards, so what should be clockwise is counterclockwise, and what should be counterclockwise is clockwise. Questions or thoughts? And of course, always the fallback is build a plastic molecular model. And when you're learning, when you're starting to see these drawings on the blackboard for the first few times, and they're not yet clear, that tangible model, that model you can hold in your hand, grasp the substituents, look down the bond, that is really the thing that's going to get these blackboard drawings into your brain. All right, so let me write that take-home message here, just so you can get it in your notes. Swapping 2 substituents. Swaps the stereochemistry, and then let's try another example. All right. Example I want to try right now is 2-chloro-tetrahydropyran. And just like we did with 2-butanol, we're going to determine whether the drawing that I'm about to make is R or is S. We're going to assign the absolute stereochemistry. So tetrahydropyran, I've mentioned before, is a 5-membered cyclic ether containing 1 oxygen. Tetrahydropyran is a 6-membered ring cyclic ether containing 1 oxygen. This is the tetrahydropyran ring structure. The oxygen gets numbered at the 1 position, so the chlorine is at the 2 position. That's not priority, that's just numbering the chain. All right, so here's the structure. Let me show you how I think about it. Now, one way I think about it is to start by simply drawing in my hydrogen. Where am I drawing my hydrogen? What's the tetrahedral stereogenic center? The carbon with the chlorine on it. And that hydrogen is pointing out because the chlorine is pointing back. Which substituent has the highest priority? Chlorine. So that gets assigned number 1. Which one is the second priority? Oxygen. Third priority? Carbon. Fourth priority? Hydrogen. All right. Which way, if we look at the molecule as it's drawn, are we looking down the bond to the lowest priority substituent? No, it's reversed. 2 things we can do. One is we can flip the molecule over. All we do is rotate it 180 degrees. I'm going to pick it up and flip it over here. Now the hydrogen is going back. We're sighting down the bond to the lowest priority substituent. And we can go 1, 2, 3. And say this is counterclockwise. And this molecule is therefore S2-chloro-tetrahydropyran. Another thing that we can do is simply make a physical model. Our oxygen is just the tetrahedral construction with carbon, with the red pieces, just like carbon. The trick with the oxygen is those 2 extra sticks on it represent lone pairs. Chlorine, by convention, since chlorine is green, chlorine is typically represented by a green ball. Chlorine is a yellow-green gas, of course very poisonous. You smell it with bleach or with swimming pool water. And you can put on your chlorine and make the model. And then you don't have to worry about any sort of drawing on the blackboard. You just say, well, okay, I'll just look down the bond. The bond is pointing back. Here's the chlorine. Here's the oxygen. Here's the carbon. We're counterclockwise. And so you never have to worry about being able to visualize. And if you're proficient at this, what you can do is just keep it all in your head and say, oh, well, the hydrogen is pointing out, which means all the rules are backwards. So since the hydrogen is pointing out and we're going chlorine, oxygen, carbon clockwise, that's really counterclockwise because everything's backwards. So counterclockwise means S. And the more you practice, the more you're going to be doing this automatically. But at this point, find something that's comfortable for you and practice, whether it's starting with the models or physically doing the rotation on the blackboard or simply mentally keeping track of everything on the blackboard. more little rules. So, a couple of more little rules. One of them is how we treat double bonds, triple bonds. And we're going to pretend something. All right, here's an example where we have a double bond, and I have an OH going out and a hydrogen going back. What we're going to do is pretend that this carbon here, the one I'm pointing to, the one of the double bond, instead of being a double bond, is bonded to a second carbon. And ditto for this one. So what we're going to do is pretend that our structure is like this. All I've done is to go ahead, and I'll draw in the hydrogens too. All I've done is to say a double bond counts as being bonded to not one carbon, but two carbons. In other words, on this substituent then, we say this substituent, instead of counting as having one carbon attached to it, counts as having two attached to it. So this carbon counts as having a carbon, and a hydrogen attached to it. Whereas this substituent here counts as having a carbon, a hydrogen, and a hydrogen attached to it. Does that make sense? So, the idea for dealing with double bonds is simply, it's just a way of keeping track. Saying two bonds to another carbon counts as two carbons. I always just in my mind just draw a second carbon, but you can also say, all right, well, we're going to count this carbon twice. So we're going to say that this carbon, since it's got one bond to a carbon and another bond to a carbon, it counts as being attached to carbon, and hydrogen. This carbon counts as being attached to one carbon and two hydrogens. And so our prioritization at this point is that the OH group is number 1, the hydrogen is number 4, and by this convention, the double bonded carbon now counts as number 2, and the single bonded carbon counts as 3. And so when we assign stereochemistry, we're citing down the CH bond, we're going clockwise, and so this molecule counts as being our stereochemistry. In other words, this molecule counts as R 3-methyl 1-pentene. Nomenclature here, you haven't learned yet. This is a nomenclature for alkanes. It says that the double bond is at the 1 position. Obviously, the 3-methyl is just like our nomenclature for alkanes. It says the methyl group is, whoops, Actually, the example I was going to do for that was simply same issue here. So I'm going to skip the nomenclature of this molecule because this molecule becomes pentene becomes 1 pentene. If you want to know, it becomes R1 pentene 3 all. But the main point, don't worry about that nomenclature. The main point is for our stereochemistry. All right, one more example with carbon-carbon bonds. So we said a double bond counts as having 2 carbons bound to a carbon. A carbon-carbon triple bond counts as having 3 carbons bound to a carbon. Yeah? Yes, they Why do I just prioritize this carbon? Because we have 1, so the question is, why do I just prioritize this carbon? We have 1 tetrahedral stereogenic center. I look at the 4 substituents attached to it, and I say we have chlorine first priority, oxygen second priority, carbon third priority, hydrogen fourth priority. So I never have to go out. We never have to have our little runoff election saying there are 2 carbons attached. If I had a molecule like this, let's say with an isopropyl group and a methyl group attached, then I'd have to start to say, we have 2 carbons, but which carbon is higher priority? So it would be 1 for the chlorine, 2 for the oxygen, 3 for the carbon with 2 carbons attached to it, and 4 for the carbon with only hydrogens attached to it. Does that make sense? As long as we are only dealing with elements of different atomic number, we never have to go on further down the chain. And of course, with 1 tetrahedral stereogenic center, we're only worrying about what's attached to 1 carbon. Could what? Could this carbon be the 3rd substituent, but it's not attached to the tetrahedral stereogenic center? Everything depends on what's attached to the tetrahedral stereogenic center. Let's try 2 more examples with double and triple bonds. I'll start with a triple bond. And let's take this compound here. So just as with a double bond, we pretended that we had 2 carbons attached, 1 for each of the bonds. With a triple bond, we pretend that we have 3 carbons attached. So in other words, now we're in a situation where we go and say, this is like, I'll again write pretend, carbon bound to a carbon, but with 2 carbons attached. Oops, doing methyl here. And so now, in prioritizing, obviously hydrogen is the lowest priority substituent. Obviously, the hydrogen gets priority of 4. The carbon that's the triple bond, we count as having 3 carbons attached to it. So we count this as having carbon, carbon, and carbon attached to it. We count this, the ethyl group, as having carbon, hydrogen, and hydrogen attached to it. And we count the methyl group as having hydrogen, hydrogen, and hydrogen attached. So by this little convention, by this little way of pretending here, now we go first priority for the acetylene group, the triple bonded carbon, second priority for the ethyl group, third priority for the methyl group. And so this stereocenter clockwise is R. And of course, you don't have to have any hydrogens attached to your tetrahedral stereogenic center. You could have all carbons attached. You could have a carbon atom with a methyl group, an ethyl group, a propyl group, and a butyl group. And you would just keep moving along the chain. The methyl group would be lowest priority. The ethyl group would be next lowest priority as you move down the chain. The propyl group would be next, and the butyl group would be highest priority. So you just continue along comparing until you get a difference. Let's try one more example with a double bond, but this time I want to make it a double bond to oxygen. And so I'll draw an aldehyde. And I'll give us an alcohol group. And this aldehyde has the same type of conundrum. We have a tetrahedral stereogenic center. I put my finger onto it. We have a hydrogen. The hydrogen is lowest priority. Conveniently, we're sighting down the bond to the hydrogen. Now we have 3 carbons. A methyl group has H, and H attached to it. The carbon with the OH group has O, H, and H attached to it. The carbon that makes up the aldehyde also has an oxygen and a hydrogen attached to it. But just as we pretended in the carbon-carbon double bond that a carbon-carbon double bond meant that there were 2 oxygens attached, 2 carbons attached, in the case of a carbon-oxygen double bond, we pretend that we have 2 oxygens attached. In other words, we say it's O, O, and H. We treat our aldehyde, we treat this as equivalent to, with the carbon having 2 oxygens attached. And so this particular example, our priorities go 4, 3, 2, and 1. And so our stereochemistry here, it's counterclockwise. We're conveniently sighting down the bond. It's S stereochemistry. All right, when you have 2 isotopes, and almost invariably we're talking hydrogen and deuterium here, you can also have a tetrahedral stereogenic center. And so I'll give us one example where now we have 2 isotopes of hydrogen attached to 1 carbon. One of them is deuterium. Deuterium is H2. It's heavy hydrogen. Regular hydrogen is H1. Not surprisingly, higher atomic mass counts as higher priority. And so our deuterium gets a priority of 3 and now we go 1, 2, 3. This isotope, or this molecule with isotopes, has an R stereochemistry to it. Pardon? What is deuterium? Deuterium is, I'll explain while I erase the board. Deuterium is an isotope of hydrogen. It's present in 1 part in 7,000 in everything, in water, in your body, all over the place. And deuterium is simply often put in as a label into molecules. So you can make molecules with 1 deuterium in it. It's called heavy hydrogen. All right, last time we drew some structures of cyclopentanol, of methylcyclopentanol, and I want to show you a trick. So last time I permuted the stereochemistry and drew out 4 different molecules. And I called them A, B, C, and D. And I think I drew them like this. And I just want to show you how we can very quickly assign the stereochemistry to all 4 of these molecules of 2-methyl 1-cyclopentanol. The trick is we only have to assign stereochemistry to 1 of them, and then I just watch what I do with the stereocenters. So remember, this molecule was 2-methyl 1-cyclopentanol. And I'm just going to start with the molecule on the left. In my previous lecture where I had all of these and I projected them, I called it molecule A. And I'm going to start with the stereogenic center at the 1 position. The oxygen is priority 1. The hydrogen is priority 4. We now have to look at the 2 atoms attached to that stereogenic center. The carbon where my finger is has a carbon and 2 hydrogens attached to it. The carbon where my finger is here has 2 carbons and 1 hydrogen attached to it. In other words, the carbon at the 2 position is priority 2, and the carbon over here is priority 3. We're sighting down to the bond, to the hydrogen. We're sighting down the bond to the lowest priority substituent. So this substituent is R. That's this stereocenter. I'm going to redraw the molecule, same molecule, but now we're going to focus on the other stereogenic center. On this stereogenic center now, our hydrogen is still lowest priority, lowest atomic number. Now we have 3 different carbons attached to it. Carbon, carbon, and carbon. The methyl group has all hydrogens attached to it, 3 hydrogens. This group, the one at the 1 position of the ring, has an oxygen, a carbon, and a hydrogen. Oxygen is higher priority than anything else in the molecule. This one here has a carbon and 2 hydrogens. So this substituent becomes priority 1, priority 2, priority 3, And so this substituent, this stereochemistry is S. This allows us to assign all of our stereochemistry. This molecule is 1R, 2S, and then 2-methyl-1-cyclopentanol. The next molecule, I've inverted both of the stereocenters. I've swapped the two substituents, the hydroxy and the methyl groups. This molecule is 1S, 2R. The third molecule, we kept the original stereochemistry at the top one, but swapped the second. So this molecule is 1R and then 2R. And the last molecule, we've swapped them around again. Let's see, is that right? Yes, 1R, 2R. And the last one is 1S, 2S.